Sure. Okay.
Right. Just skip over explanation to state the result. And then we can also
Okay, so theorem G T star E acts on the equivariant cohomology string union over all D modular space. This is simple. The action agrees with the VOA action described before when F is equal to all of the divisor of infinity.
before.
On Wednesday, so the given at the beginning of the talk, right?
Yeah, we are lifting this action, right? So the theorem states whether we have successfully lifted this action.
Yeah, so that I defined like a vertex operator algebra as cohomology groups were the same as whose weight spaces were the same as the dimensions of these cohomology groups. And I described an action, a cyclic action of a Lie algebra on the vacuum module for that VOA. And I'm saying that the action defined like geometrically agrees with the one from the VOA under that under an isomorphism between these cohomologies and the weight spaces.
And then for this F and like the horizontal thing, that would be like Chiraco's action,
or the kind of the field directions in the VOA, so kind of the vertical ones. So here we have, yeah, so the one that corresponds to points. This is Chiraco. And this is, yeah, the weight spaces of our vacuum module go this way. And here we have our coordinate B, here we have our coordinate A, and W, A, B, gamma acts this close. So yeah, and in particular, yeah, they're related by this SL2 Z action.
Can you explain this a little more because I'm not following.
Sure, yeah. So
yeah, I left early Wednesday, so sorry.
So we have a module who kind of has an integer's worth of highest weights. So this VOA, let's just, I don't remember what I called it at the beginning, we could call it like V T star E, is isomorphic to, it's charged by a lattice isomorphic to the integers, which I want to think of as the elliptic curve direction of the first string class of an elliptic curve. And then here we have a Fock module on free superbosons, which is the cohomology, the cotangent bundle of an elliptic curve. So on a VOA with this vector space, we have an integer copy of Fock modules. And there's an action of this Lie algebra. So that if you go in the vertical directions, this corresponds with Chiraco's action. And if you go in these other directions, we get these other generators of what are called GT star.
And vertical direction is which direction?
It's the field direction. So it's a VOA and it has fields described by Z's. And so it's, yeah, it's just the action of sort of modification by points.
So this is the he has this field kind of generators called WAB, and in the B direction, that's this is what he has on the board.
the image describes the action of GTE, right?
Yeah, the action of these arrows,
Yeah.
so the
On-
going between different weight spaces, the weight spaces
weight
is
space.
cohomology groups for various.
Okay.
So this is, various.
Um,
Okay, so then the next thing is that evaluation push forward. So for almost all data, evaluation push forward, moduli
I think you
space.
have twice the cohomology, which is cohomology.
Yeah, the cohomology.
Double.
And just making sure I understand the C of e to the e is e to the e is what is like two-dimensional lattice or
One-dimensional lattice.
what is it?
It's a sublattice of the hyperbolic lattice where we pick an isotropic direction and go in that direction. So it's, I don't know, in the string theory perspective, it's like you only have like light cone generators, which are also right.
This was the plus. That was the plus.
That was the plus best.
Okay.
We don't take, we don't take, right and left
I was
movements.
say you're only explaining the whole thing. You didn't explain the plus.
Yeah. So plus is just we only take
Okay.
the lattices going in the circle direction. And for almost all curved classes in our moduli spaces, the virtual fundamental class, where we subtract off multiple cover components of our moduli space and curved class beta, is equal to W minus, maybe already is equal to W minus beta gamma I, W beta gamma I. Gamma is a basis for the root space, and beta is canonically identified with a pair of integers. So we can calculate thermal Witten classes in terms of this algebra, which has an explicit formula in terms of the OA, explicit.
Just make sure I understand. These are U1 instances, is that correct? A U1 gauge here on T star.
Yeah, you engage theory and T star, yeah. But the so the T duality sends it to like UR gauge theory for any R.
Yeah.
So it's also, R can be R, so R can be arbitrary. All right, and then finally, the
Wall
same.
of stone is like before the wall except for one line, or what's the wall of stone?
It's still the same. The roots that correspond to this horizontal direction. So yeah, everything except for those that are multiple of the curve that traces the elliptic fiber that correspond to these roots where b is equal to 0 and a is an integer. I have the entire purpose of this project was to calculate the contribution of those roots, and I've still failed to do so. But conjecturally, the same formula is exactly the same.
Does it checks on the computer already, or
Some stuff checks on the computer. The computer does these things actually very slowly, and there's a tremendous number of signs that you need to get right. But I would say like a considerable amount of computer evidence, but not perfect computer evidence.
I'm sorry, say again. What is the hard case?
The hard case is like perpendicular to the
I still don't. Can you say geometric as opposed to perpendicular vertical to that? I still
it's
don't.
horizontal in this picture? Horizontal. If you move directly horizontal.
So we can get curves in these moduli spaces of instantons where our curve. So that we're only dealing with the genus 0 case, but the curve is the same class as a genus 1 curve, where we just have our instanton, which is a point in T star E wraps an elliptic curve, and then where we have several of those, the same class of these can degenerate to something of genus 0. And those are the hard ones to calculate the contributions of. So
So
Yeah.
you're counting what? Genus 1 curve in
Genus 0 curves, but they're like genus 0 curves that lie in like linear systems of like higher genus. And those are the ones that are hard. So these have elliptic fibrations. So in particular, these moduli spaces. So M is like an elliptic fibration with some like highly singular fibers, and then it also has smooth fibers, which are n-dimensional tori. And the hard curve classes are the ones that actually like also live on generic fibers and degenerate to some sort of horrible like singular thing. So these are the hard curve classes there. That the class corresponds exactly to like an instanton trace is an elliptic curve, but in our moduli space, it does this in such a way that it's actually a genus 0 thing doing some complicated singular stuff happening.
So your moduli space has a torus vibration over some place?
Yeah.
Integral.
So that's just like in the Hilbert scheme of points on T star E. You just take its support and then figure out its support over the base A1 factor. And this is like a compact Lagrangian fibration over the base. And a curve that actually like has the same class as one that lives in one fibers, so hard to understand.
What examples of this are not like that? What are the easy ones?
The easy ones are, for example, like if you just have like a fat point and you have a P1 of 2 that wrap around, this is kind of easy. And then the vast majority of its like T duality conjugates are also like just as easy. They're just sort of fat points on like UR instantons for R greater than 0. This corresponds to like instantons where in rank 0. Yeah, so that in a duality frame where we actually have like instantons, it's rank 0 sheaves. So it's yeah, these are the ones that are kind of harder to study. Yeah, rank 0 instantons.
But in principle, there should be just the flatness of the connection should constrain those.
Yeah, the flatness of the connection and the fact that sitting inside of GT star we have a whole bunch of other copies associated with lattices. So yeah, I expect that we also have like GT star for some like sublattice sitting inside Z squared, and then yeah, the flatness of the connection together with the fact that each of these is the same Lie algebra, and so the Casimir for a generator of this commutes with the Casimir for the subalgebra, together with the flatness connection should identify it with this operator. But this is still a work in progress. The connection is actually like extremely complicated. But part of its complexity is related to this, that if we take the stabilizer of this, stab is sitting inside of the duality group, fixing the Turing class of our sheaf, it acts equivariant. Yeah, so if we take, so let's step this, then the quantum connection is step B equivariant. Which imposes a whole range of dualities of the like quantum connection. In particular, it's in general some infinite dimensional, some like infinite Weyl group. And similar stories have been used to prove like the modularity of like generating functions of enumerative invariants for the Hilbert scheme of points on K3 surfaces. So this should be related to some sort of quasi-Jacobi property for the generating functions in the T star E case.
Well, that's a very strong constraint because usually the usual suppose you knew that this kind of flop invariance of the connection.
So it's different from flop invariance. So flop invariance is analytic continuation. This is like in particular the nothing like acts on the Kähler moduli space. Flop is just analytic continuation in the Kähler moduli space.
But it just means what the flop invariance goes to. Z goes to 1 over Z, this type of thing, right? Is that not where Z is your Kähler variable? You don't have that sort of.
Yeah, it acts exactly like that.
Yeah. So if you're doing Z to 1 over Z, then this kind of thing spits out, some very predictable thing, and it has to match the change in the classical operator.
Right, yeah.
And
This
that
is
fixes, and that fixes whatever the multiple of that operator is.
Right, yeah, I agree with that, yeah. But it doesn't do anything about these curve classes. So the stabilizer of the it just doesn't do anything at all to these curve classes.
So the curve classes that you
the bad ones, yeah. The bad ones are basically entirely insensitive to the stabilizer. And that's kind of why they're bad. So yeah, you get no control over them by this web with invariants.
And what was the purpose of having 2, 3, 4, 6 there?
It's just the dimension of our the algebra press 2. So
No. The purpose of having that table is that you say that the storage generalizes to those types too, or
Yeah,
somehow plays a role in the proof?
it plays a role in the proof. Yeah, and and then a lot of these also have analogs for this case. Yeah, it actually is important to use those cases for the proof. The story is that you can identify convolutions of some correspondences up to a particular complex number, and you identify the complex number using isotropic roots that you can get as products of real roots. And the real roots follow from a VOA calculation where you can identify these the specific complex numbers that are the multiples of convolution. So you need to use the real roots in order to identify the no real roots case.
That if I just take the classical multiplication of the sandwich, what does it look like? Is that somehow some magical system we can somehow relate to in some way? Or?
It's something like it's an extension of the Colordro-Sutherland operator. It with kind of 2 extra variables. So it seems to be something like, I don't know. We take classical. So here's our Taylor moduli space. So here are an infinite number of walls. As we tend to just sort of classical multiplication in one chamber, we get n equals 2 supersymmetric extension of the Colordro-Sutherland model together with sort of this constraint equation. And then we also get.
But Colordro would be just acting on in that vertex algebra thing. Okay, the odd variables, that's the homology variable, that kind of supersymmetric extension business.
Yeah.
But this this lattice direction business, what does it do to Colordro there?
So we also have the other the same thing that it does in these really sort of simple operators, that if we take these other C1 of lambda I, there are operators which are the integral of alpha of delta push forward of divisors corresponding to fundamental co-weights. Alpha squared this Z. Are these sort of other operators? They commute with the Colordro-Sutherland operators. And so the strange thing about this duality is that the duality exchanges the Colordro-Sutherland operator with these. So as we go to here, we get so the usual Z goes to Z inverse duality is this, but then we also get all of these other dualities at a bunch of these other planes corresponding to precisely the stabilizer. So we also get all of these other limits which are n equals to supersymmetric Colordro-Sutherland. So it's some complicated sequence of limits of the Colordro-Sutherland system that's as you take an infinite number of limits, they're described in different ways depending on the geometry.
And then lens Virasoro is just like super extension of this, and like n equals 2 super extension.
I don't know if.
So sorry, you have like a super extension of lens Virasoro here.
Yeah, you can, is the same as, yeah, you can write this C1 exactly as that. I mean, Lane literally describes this for any surface. So, yeah, it's with, yeah, n equals 2 labels. Not certain this is the exact same thing as like n equals 2 superconformal algebra. It's maybe better to think of it as just Virasoro with cohomology labels in this cohomology group.
Okay, more questions? Okay, one more question I'll ask you privately.
But what's the plan with just finishing the proof?
The proof, I mean, I was gonna, I wasn't.
Maybe we should.
Is it a secret part?
No, I don't know.
Okay, let's maybe we can.
Maybe Sam would be hesitant to
Okay.
I mean, I could. You have a question?
No,